Okay, so you submitted the project, and the ranks are pretty thin today. I think it's probably people who are up all night working on the project at the last minute.
We're here.
Now they're hunched over. You guys are still here, huh? Yeah. All right. So the project is finished. Hopefully that's a relief to have it done. I always kind of hated it when I was an undergraduate student. All of the projects were due on the last day of the semester, and so I vowed that if I was ever in a position where I was assigning projects, it'd be like staggered back a couple of weeks. And now you can focus on all your other projects you still have to do. We've got a couple of homework assignments that are still on the horizon, but definitely the intensity for this course is winding down. You know, the volume of work, you're already over the hill, and the intensity of the concepts is also relatively simple from here on out. We kind of crested when we were talking about external rate of return, you know, like incremental analysis, the economic service life. Those are probably like the most complicated things that we had in the semester, and from here on out it's relatively straightforward concepts. So congratulations, you made it. I was really impressed. Some of the spreadsheets I've looked at already, they were great. Maybe I was just seeing the people who were far enough that they were proud to show me their work, but so maybe it's not a representative sample so far, but honestly, I don't give false praise, but so far what I saw was better than any previous semester where I'd looked over the spreadsheets in advance, and so I'm actually not dreading having to grade your projects, and I'm not always able to say that, so I'm not dreading your work. So great job. It's, you know, there's 40 plus students in the class, and so it's going to take me some time to get through all those, especially because I really do want to be pretty thorough in looking at and considering all the work that you put into it. And so I'm not going to be able to, you know, tear through all of them this afternoon, but certainly well before the final exam, you're going to know what your course average is, including the project, so that you have a pretty good idea of where things are at prior to the exam. And of course, the weighted average that you can find in the gradebook already includes the effect of dropping the 2 lowest homework scores. And so, you know, with the exception of the project, the averages are pretty well stabilized on where they're going to be. All right, so homework 15, which is related to this cost estimation stuff we've been doing, that assignment's not due till a week from today. And we're going to address another factor, another technique that can be applied to do cost estimation, that's the learning curve. Any announcement-related questions before we move on? All right. So here we have a picture of a sweatshop. And it's called a sweatshop, I guess, probably because it's uncomfortably warm in there. They're not spending a lot of money on the air conditioning. It's a garment factory where, I don't know if you've seen video. I really ought to track down a video of how quickly these people can sew a pair of pants. It's like they're zipping through the seams in like 1 second for an entire pair of pants. And I took home economics when I was in high school, and you know, we had to sew a pillow. Probably a lot of you had the same thing where you had some sort of a little sewing project, and I came to appreciate how quickly a real professional is able to do something that I'm pretty slow and clumsy at. And that's really at the heart of what we're talking about today, the fact that when you gain experience, you're faster at doing something, regardless of the task, whether it's sewing pants or preparing for lectures. My first semester that I taught, I'd probably spend about 5 or 6 hours preparing for each class, and now I spend about 5 or 6 minutes preparing for each class. And maybe that's obvious to you, but I think part of it is just that I have my notes already developed. I've got the in-class exercise that I developed in previous semesters, and so I can hit the ground running in a way that I definitely couldn't the first time I did something. So there's a formula I'm going to be showing you later, and the first concept I want to introduce is the idea of this K value is how long it took you to do something the very first time. And so let's just say, for instance, I don't know this person, but let's just say that the first time she sewed a shirt, it took 12 minutes. And so in order to estimate how long it's going to take to do something in the future, the baseline measurement you begin with is how long did it take the first time. And then what this formula does that we're going to be working with today is it says you're always going to be getting slightly faster. Now at first, your learning is fast. The slope of the learning curve is very steep at the beginning because you're making huge improvements. You're finding all these really obvious ways to get better at what you've done. And then the longer you've done something, the improvement gets incrementally smaller and smaller because all the low-hanging fruit has been picked, so to speak. But the first thing that you start with when you're trying to predict how long it takes to do something or what other, it's not always just time. The same approach can be used for input materials besides time. It could be used, for example, in manufacturing processes where you're wondering about like wasted lumber in building a house. And so the first time you build a house, maybe you're not quite as sophisticated at measuring how much lumber you need, so there's going to be a lot of leftover scraps. And then as you get more experience, you avoid the wasted materials. And so that same kind of principle can apply. And here what we're saying is the first thing we measure is the first time it took. And so the next idea that we're going to introduce in the idea of learning curve is some sort of ratio of how much time it took to double your productivity, your total cumulative productivity. And just as an illustration, let's say that this guy is installing oil pans. If we knew how long it took to install the 5th oil pan and the 10th oil pan, what we would say is going from the 5th to the 10th, he's now doubled his cumulative productivity. Going from oil pan number 5 to oil pan number 10, your experience has doubled in between that interval. The same thing would be true going from the 1st to the 2nd, or from the 2nd to the 4th, or from the 4th to the 8th. I think you probably sense the pattern here. You time how long it takes to do something one time, and then when you've got twice as much experience, you time it or measure it again, and then you take the ratio of that. So what this says is that every time he doubles his experience, it only takes him 92.5% as long once he's doubled it. So that is the variable S that we're going to use in our equation. Now these are both illustrations that are using people as an example. I think that these same principles also apply when it comes to automation. And I just want to show you a video that illustrates a future that I think is going to become a lot more widespread in which people are less important. All right, so that's kind of interesting to see the automation that's involved and how few people are working in that warehouse. You know, if you had made a video of a warehouse even 10 years ago, it would be loaded with people and it would be very noisy and chaotic. But those little robots are moving the inventory actually to the person who's picking it out of the cabinet. And so the person doesn't go and get it out of the inventory, but the whole shelving system is constantly moving around in the warehouse. And so it seems undoubtable that these same learning curve principles can be applied to automation as well, that the amount of time it takes from when an order is placed to when that is shipped and ready to be picked up by the delivery company, the time keeps getting smaller and smaller and smaller. And you can actually kind of notice that. When I purchase things on Amazon recently, it's been telling me that I can get it the very next day rather than 2-day shipping. You know, I've got Prime, and so I've already become accustomed to 2-day shipping, but now it's ready for next day shipping as long as I order in the morning. You know, so if you order before like noon or 1, they're able to get their robot overlords working fast enough that they can get it picked off the shelf and boxed up and ready for you, the post office, before the end of the day. So it's kind of interesting to consider what automation is going to do and the types of jobs it's going to destroy and the types of jobs it may create over time. All right, so we've already talked about the first factor is K, the baseline time it takes, and then this S curve is the percentage of time that is reduced when you double your experience. All right, here is a graphical representation of the learning curve. And so if we have on the horizontal axis the number of units that have been made cumulatively over time, you can think of this as our experience. And then on the vertical axis is the amount of input required in order to do the task. And time is probably what we'll talk about most as the input. And so The more experience you get, the less time that's required, but what you'll notice is that the big gains are early on, that curve is very steep at the beginning, but then it's starting to flatten out so that it's harder and harder to find new ways to save time or to save money or save materials. This is sometimes also called an experience curve or a manufacturing progress function, depending on the textbook. So here are all the formulas and definitions that we're going to need to do calculations related to this. We've already talked about K and S. Now we use S in order to calculate what's known as the learning curve exponent. And so in the formula that we're going to be applying, you actually calculate some n value, and so you do the logarithmic function to S. Remember that S is a decimal, and so you do the log function to S, divide it by the log of 2, and that's how we come up with the learning curve exponent. And then this function is used to produce how much time or what inputs are going to be required for a certain unit that you've done. So, if you're sewing shirts and you want to predict how much time will it take you to sew shirts by the time you've made 100 shirts, you could use this function. And first, you'd need to have a little bit of data to get an idea of what the shape of this curve looks like and what was the first amount of time that it took. But then once you have that, you can extrapolate into the future. And let me give you an example of how we use this learning curve function and the equations. Let's say that you're sewing pants and your first pair takes 85 minutes. So what that means is that K equals 85 minutes. And the second pair of pants you sew takes 76.5, and the fourth takes 68.85. So to go from the second to the fourth, that's a doubling in experience. It's also a doubling in experience to go from the first to the second. So we could set up S as either 76.5 minutes divided by 85 minutes. So that's going from the first to the second. And if you calculate that, you'll find that the S value is 0.90. So every time you're doubling your experience, your total cumulative experience, it's only taking you 90% as long. Just as a check, since we've got the data, let's also see what if we had calculated S on the basis of 68.85 minutes divided by our second, so that was 76.5 minutes. Has someone got a calculator handy and tell me if this holds up so far, if the behavior is following this nice even function? It's 0.90 again? All right, good. Now in the real world, it may not be a perfect fit. Every model is a little bit fuzzy. Some work better than others. Some models predict reality pretty well. Others are just really a crude approximation. And so, don't be thrown off and discouraged if you try and apply this in the real world. And, if you go from the first to the second, maybe it's 0.92, and then from the second to the fourth, maybe it's 0.876 or something. And you'd maybe just average the two, and you use the data. You do the best you can with the tools and the information you've got. But anyways, this is a perfect example because I created it that way, and S is 0.9. So what we do with S, now we have to calculate the learning curve exponent, n, log of S divided by the log of 2. Okay, so the log function of 0.9 and then the log function of 2 is going to give us, up in the numerator, negative 4.5757 times 10 to the minus 2, and then in the denominator 0.30103. So that means that n is negative 0.1520. We've got all the data we need now to predict. The question is asking in part A, how long will it take you to sew your 10th pair of pants? So what that means is, in part A, U is 10. We want to find out the 10th pair of pants. And so That means when we substitute it into the formula, Z sub 10 tells us the amount of time to sew the 10th pair of pants. So that's K times U to the power of N. So that's 85 minutes times 10 to the negative 0.1520. Okay, so that's 85 minutes. And then this other function is 0.70469. So compared to the first time we sewed pants, by the time we sew the 10th pair, we're going to only require about 70% as much time. Because of all the experience we've gained and all the shortcuts we've learned, we're sewing through our hand less often and all those improvements. So it only takes us 59.9 minutes to sew the 10th pair of pants. So Z sub 10 is 59.9. Any questions so far? Let me pull that up on the screen for your colleagues who are still fast asleep. Let's see. Assuming they watched the video. Oh, you know what? I may not have that here. I'm going to have to find that later. But I do want to answer part B on the computer because it's asking in part B the total time required to sew all 10 pair of pants. So in part B, it's asking us to solve for Z sub 1, Z sub 2, Z sub 3, Z sub 4, and add them all up. And rather than do that on paper and by hand so many times, we can automate it to make things a little bit easier. Let me paste the formula here into the spreadsheet just so that we can see what we're doing. That's the formula. All right. So I've got a certain pair in question, and then the time it takes for that pair, and we're starting with the first, the second, the third, the fourth, and so on, down through the 10th. Okay. Let me just off to the side define that we had S was 0.9, and then we had calculated N was negative 0.152. Okay, so the first pair was given. That was 85 minutes. The second pair, I'm just going to use this formula. It's K, anchoring that reference because it's always going to be the same amount of time for the first pair, times U, and U is which pair we're on, so the second pair, to the power of N. And I'm anchoring that reference as well. Okay, so 76.5, and I think that was some given data, so that matches up nicely. We don't necessarily need to see all those significant digits like that, but if I drag this down, now it'll calculate all of them, including this 10th pair that we did on the board, and we got 59.9 minutes. And so the question asks, how many to sew all that first batch of 10 pants? So the total amount of time for your first 10 pants is 679 minutes. So a little more than 11 hours. That's the basic idea with the learning curve. And I have an in-class exercise for you where you need to apply these ideas to a Rubik's Cube. And the trick, though, is that you forgot the first time you did it. You've got some data, but you don't have the very first one. You don't have K. I'm not going to tell you right off the bat how to handle that. I want you to see if you can figure out what to do when you are missing some data. How you can fill in the blanks. So we're missing the data for the first pair of pants. We don't know K, but we can apply the pattern forwards and backwards, that the improvement with the doubling of experience to go from 2 to 4. We could calculate the S value and check it going from 4 to 8. Yes, it's the same S value moving forward. And so what we can do is project backwards and say that the first time we made pants, it took, well, we divide by 0.91 to get 24 minutes. And so the ratio of 24 minutes to this K value that we calculated of 26.38 follows the same 91%. So that gives us K is 26.38, and we want to know how long it takes the 100th time. And we use the learning curve exponent. It takes 14.09 minutes. Will it take exactly that? There's obviously other factors in play. You know, whether your fingers are sore, whether you had a good night's sleep the night before, whether there's noise playing. There's a lot of other confounding factors, and so I don't want to assume that this learning curve function is the only thing that applies in estimating what inputs are required in order to estimate costs. But it is just one trend and one factor that you can account for and kind of work into your estimations when you're trying to prepare a guess of what projects may cost. All right, so we are finished for today. Just remember that it would be a great use of your time to get an early start on that homework assignment while some of the material is still fresh in your mind. It's due a week from today. We'll continue our discussion of cost estimation in class on Monday. So have a good weekend. I'll see you then.